All right, this video is going to introduce us to a set of really important equations called the kinematic equations. I'm actually going to do what's called a derivation here, which means I'm going to show you um, where these equations are coming from a little bit. And we don't do it a lot in this class, but this one is, gives you some sense of the sort of physical roots of these equations. So you don't just see them as a bunch of different numbers. So we'll start with a real basic situation and try to build that into a set of useful equations. So we're going to start trying to figure out, we're actually going to derive these equations because it's a relatively straightforward derivation. And I just want you to see basically just how, in some ways, common sense these equations are. So we're going to imagine an object, a dog or a rabbit or a potato, is traveling at a constant velocity. Um, let's go with the dog. That's a little easier to think about. Um, we can observe that during a time period delta t, the object goes a distance delta x equals velocity times delta t. This is as simple as a car that's going at 60 miles per hour for half an hour has gone 30 miles, right? 60 miles per hour is our v, half an hour is our delta t, and 30 miles then is our delta x. When we want to graph that, if we have this constant velocity, we find that um, this term, v times t, is just the area under the graph, right? And that makes sense. You're multiplying the x-axis times the y-axis. So a span of delta t here, so this line, times this constant velocity. So really we've just made a rectangle. We've defined one side of it as v and another side of it as delta t. And so that area is going to be equal to our delta x. This is similar to last time we talked about the slope, right? Tells us the acceleration. So the slope of this line tells us the acceleration. Well, if we go the other way, uh, instead of using the velocity plot to find acceleration, if we use the velocity plot to find position, change in position, then we want the area under the curve instead of the slope. So that's one equation. Now let's consider the fact that line might be sloping. So what does that mean? Well, that means the velocity isn't constant, but is the slope of this line changing? No, the slope of the line stays the same. And what that means is that our acceleration is constant. So this is a plot of a constant acceleration movement. Um, it's not a zero acceleration like our previous example, but it is a constant acceleration. We can still find the area traveled by finding the area under the curve. It's a little more complicated here, but not terribly. If I want to find, like if I start at time equals 0 and I want to find the area under this curve, well, I'm going to find the area in the blue rectangle, right, are my initial velocity times t. But then I also want this red area, which is a pretty simple triangle, right? It's still that delta t times the difference between Vf and V naught. So here we do some algebra. Here's the area of that blue rectangle. Okay. Here's the area of that red triangle. Vf minus V naught, which is this, times delta t, which is that, times a half, since it's a triangle. Then we do some algebraic rearrangement, and happily, some things kind of disappear. And we end up with this equation down here, which is our first real interesting kinematic equation that tells us we can find, even when our velocity isn't constant, as long as our acceleration is constant, then we can find our delta x. All right, so what else can we observe about the case of constant acceleration? Well, let's go back to our average velocity definition here. Remember, this is just our initial velocity plus our final velocity, and halfway in between, that's going to be our average velocity as long as acceleration is constant. Now look at the earlier result that we found on the previous slide right here, and you see some similarities, right? This term is the same as this term. And so this allows us to combine those two equations to get this, which is that our average velocity, so basically all we did was take this and replace it with the other side of this equation. So I put, this became V bar here. And what this says is essentially what we said 2 slides ago about velocity and time. Remember the 60 miles per hour for half an hour. Except now we're saying, well, we can just use average velocity. Even if our velocity isn't constant, we can find the change in position by using our average velocity. Let's then throw acceleration in there. We define average acceleration as this, which is the total change in velocity divided by the total change in time. If we rearrange that, so I'm going to multiply by delta t and bring that to this side, and then add v naught to bring it to the other side, we end up with this equation, okay, which tells us essentially that our final velocity is our initial velocity plus the change in velocity created by our acceleration. So our units here are length per time, right? This is length per time squared, but we multiply it by a t to get length per time again. And so our equation is nicely dimensionally homogeneous. And so let's sub this equation again into our displacement equation. So this was our displacement equation that we just found. And we're going to take this VF, and we're going to replace VF with V naught plus A times delta T. So we get a more complicated equation here, but again, happily, we see that we have 2 V naughts in here, and so we can start to combine terms. And we end up with this equation down here. Delta X equals initial velocity times time plus this term that has to do with acceleration. So this is saying basically this is what you would have traveled if you continued at the initial velocity for that delta t. And this is the change in that that's created by the fact that you're accelerating, either positively or negatively, right? If this acceleration is negative, then our distance traveled is going to be smaller. If we're accelerating positively, then our velocity is increasing and our distance traveled is going to be larger. And then finally, we're going to put our definition of acceleration in terms of delta t. Okay, so what we did here was just, we had A equals total change in velocity over total change in time. We moved total change in time over here and then divided both sides by acceleration. And then we sub that into our nice old displacement equation. So I'm going to take this delta t and replace that delta t with my right-hand side. And this looks messy, but again, it's not all that messy, right? We have these two terms, which is going to give us a quadratic equation, but the middle term is going to disappear. And we end up with this equation here, that delta x equals this guy. And then we can rearrange that, and we normally write it this way. So we want to know what our final velocity is in terms of our initial velocity and our acceleration. This one is a little less intuitive in terms of the way that you can look at it, but it still makes sense. We have initial velocity, and then that's changing depending on how far you've gone and how fast you're accelerating. So that gives us our set of equations here. We're going to make a couple of changes to it. We're going to just change it into a 1D equation. We'll change it back into 2D later. We're going to assume that our T naught is 0, so we're just going to call delta T T. And then we'll make another little small change. And these are our kinematic equations. Notice these comes from simple observations, okay, about how fast you move over amount of time, and an assumption that acceleration is constant, okay? So if your acceleration is not constant, these equations no longer work. Okay, not all of them, any of them that have acceleration in them. Okay, how do we use these? Well, there are 6 variables, VF, V naught, XF, X naught, A, and T. Why don't we have an A naught and an AF? Because we've defined acceleration as constant, okay? So these are always going to be the same, so we just call it A. Notice that all of these equations don't contain all of the variables, right? So this one doesn't have an A in it, this one doesn't have a VF in it. And that allows us to use these to deal with different situations because we're going to have an unknown that we want to solve for, but we're oftentimes going to have another variable that we don't know in the problem. And so we can choose our equations based upon what we want to know and what we don't know. Okay, and you'll get better at that. That just takes a little practice using these equations. So let's try that. The first thing is write these out on a piece of paper you can access real quick because we'll use these not only in this unit but really through the whole term and into 152 in various circumstances.